afternoon, everyone. So, few of you might know me as well, as I've delivered a lecture a few days back on low power cells, right? So today I'll be delivering a lecture on the topic. As you all know that this would go not a one-way session. I want you to be interactive and like unmute yourself. Don't unmute all of them in one go because it creates a noise, but let it keep as a interactive session, not as someone who's delivering the lecture and you are only the one who is at the receiving end. Okay, let it make it as an interactive session. So to begin with, like I assume that all of you are kind of in the VLSI field, right? So you would have heard about the terminology called as RTL to GDS, right? Correct. So can any one of you just let me know what does the RTL stands for?
Register transfer logic.
Register transfer language.
Pardon? Hello? Okay, yeah. It stands for register transfer language or register transfer logic. Okay, and what does this GDS stands for? Have you heard about this terminology, GDS or GDS2 format? Correct? So what does this GDS stand for?
Graphic data system.
Okay, correct. It stands for graphic data system, correct? So now, when you know that there is a complete process, like when you say it's RTL to GDS flow, right? The input that comes is something which is called as RTL, okay? Then it has to be processed and the output is generated in the form of GDS. Now, every input, every output has some formatting, okay? It's in some, either it can be in form of a language, it can be in terms of SKI, or it can be a binary format, okay?
Yeah.
So,
are you sharing the screen? Are you sharing the screen?
I'm sharing the screen, just, yeah.
But it is completely white almost.
Yeah, I have to start it. I'm not.
Okay,
I'm
okay, fine.
giving a brief overview of what the topic of the session will be. Okay, so fine. So, any one of you, like, since you are either in BTech or you're doing your masters, right? In which format is the RTL? If you would have written the code, right? RTL is a form of descripting language. Verilog. Is it only something like you write it on only Verilog, or there are different kind of languages, right? It can be in Verilog. It can also be in a VHDL format, right? Correct. So there are different languages that can be used to write RTL. Okay. Now something is the output, which is being in the form of GDS, correct? Have you ever noted or have you ever looked upon what's the format for GDS? Anyone of you? Anyone of you are aware like what is the format of the GDS file?
Binary.
GDS. Correct. It's a binary file. It's not even SKI file. It's a binary file. Why it's a binary file is something. See, this Verilog, VHDL, the way you write this code. Okay, this is a kind of coding language for machines, right? Just like C, C++, Python is for computer engineers. The way the compiler understands for our VLSI is in the form of Verilog and VHDL. But the GDS is the file that is being which is being sent out to the fabrication unit or the foundry. Okay. So fabrication and the foundry units doesn't understand what is and what is or what is flop, right? This Verilog and VHDL is a kind of a human understandable language. Okay, I'm using an AND gate, XOR gate, flops, latches. Okay, but foundry understand only in the terms of binary language, which is 0 and 1, which depicts what is the layer, what is the transistors. Okay, so this complete flow, which is RTL to GDS, is nothing but your complete VLSI industry standard, whatever it goes through. Now it has been cut down into different steps. Okay, so the first step of converting this RTL format to an intermediate format, which is called as Netlist. Okay, so that is the process which is done by someone which is called as, have you ever heard about like converting an RTL to Netlist?
Synthesis.
Correct. So the today's topic is synthesis. Okay. So fine. So now let us say that, for example, everything, if you look into it, right, just as I explained, that everything has to be first as a form of an input, then it has to be processed down, okay, and then you will receive something as a output. So initially at a high level summary, you understood that the process that we are going to understand during this session is something which is called as synthesis. There is something which has to be provided as an input, and there has to be something that once this process do, will get it in the form of an output. Correct? Now, for example, let us let us correlate with the real world analogy. Okay. Now let us say that there is an idea in your mind that, okay, for example, if you are someone who have around an budget of 1 CR, okay. Now you are saying that I want to invest it and I'm more interested in real estate, and I want to build either a building or a skyscraper or a bungalow or something. Okay, this is your idea. Okay, now this idea, for example, a person can have an idea of like construction of building. It can be in form of skyscraper or a low-rise building or a bungalow or a row house, right? So now this is in the form of a blueprint that you have currently, okay, which is normally which you go and tell it to your architecture, right? So architecture will ask you like what are the different kind of questions. Like for example, if you have decided that you're going to build a skyscraper, okay, so how many floors it should have, correct? He will ask you like you want it of 20 floor, or you want it of 50 floor, or you want 70 floor. How much should be the number of floors in your building, correct? Where how many elevators do you need? You need 2 elevators, 3 elevators. Okay. Where should be the parking space? Okay. Where should be the garden? Where should be the entrance of your building? So these are the different kind of things which an architecture will ask you, because he needs to design the blueprint of your building. Okay. So this blueprint is nothing but this is at very high level language. It is kind of architectural specifications, right? Architectural point of view. Okay. Similarly, when you come and correlate it with respect to the VLSI field, right? There is something like, for example, there the chips can be designed for various different units in the market, right? It can be designed for your smartphones. It can be designed for your laptops. It can be designed for your computer system, data centers, or if it's a gaming chip, GPU. Okay, so there are different as we compare, like you could have designed skyscraper, bungalow, row house, right? Similarly, you can design all these things. So you need to specify what are the different kind of structure that you require for designing your chip. What are the kind of functional blocks you have? How much ALU will have? What kind of memory you will have? What are the input outputs you will have? What are the different kind of blocks you will have? Correct. Similarly, this is the architectural perspective. This is a job of architect engineer. This is done by very senior level folks. Okay, that how much kind of memory I'll use, ALU, CPU, will I'm going to use GPU, what are the different kind of memories, how will with their interaction happens. Okay, so this is a kind of architectural perspective. Now, once you have to go from a high level description to lower level description, then comes into the picture kind of specification. At a very high level, you have given the architectural inputs. Now, see, when you decided about, for example, you are building a skyscraper of, you decided like, I'll have a 30-floor building. Okay. Now you have to give the exact dimension that each floor will have what dimensions. Okay. Now let us say that you have decided you are going to use the tiles. Now you have to say which kind of tiles materials you are going to use. Are you going to use a stone perspective, or it has to be a marble perspective? What kind of materials you are going to use, you have to describe it. Okay. For example, there has to be glasses for the windows. Do you want it to be opaque, or you want to be transparent? Okay. So this is a one level deep drill down that you have to understand what are the different kind of specifications, right? If you are going to design the door, what kind of wood material you are going to use. So similarly, when you correlate it to the R perspective, it is like now you decided you have to use ALU. Okay, that is arithmetic logic unit. But how many bit it should be? Should it be 8 bit? Should it be 32 bit? Should it be 64 bit? Okay, you have to design like on which frequency am I going to work? What should be my power constraints? Okay, so this is something that is a one more deeper level to understand along with the architectural perspective. What is my specifications? Okay. And once this has been decided by the higher level architect or senior architect folks, this design is then jotted down in the form of RTL. Okay, this is what it is, kind of like a form of a concrete implementation technique. Okay, that how will I do it? So you just understood that the input that has to be provided to this process of synthesis is RTL. Okay, and the output, which I stated, right? The output is going to be in the form of netlist. This is not directly GDS. Okay, the GDS, but this netlist has to go through a PNR flow. Then PNR guys will do a lot of optimization, CTS and everything. And then whatever you have at the output of the PNR is something which is called as a GDS flow. But the main intent of the synthesis is to convert a high, whenever you read it in a dictionary format, right? Everyone, you would have just gone through it, like it is a way of converting the high level descriptive language into low level, correct? Because RTL
Ma'am,
is
excuse
something.
me.
Anyone
Ma'am,
else?
what's meant by the behavioral description, ma'am?
Behavioral description is kind of a thing like how will you see, I said, right? For example, you stated like you want to design, for example, I said it in terms of buildings, right? Now, in this perspective, in form of VLSI, right? How will your design behave? Like, for example, you can give it in the format of like state. You want to perform an adder function. Okay. Now, this adder can be performed with. There are different types of techniques, right? Full, like you can do it with 2-bit adder, you can do it 1-bit adder. There are different types of techniques, but the way it will implement it, right? It is called as the behavioral thing, right? For example, I'll explain you in very simple format. Okay, now let's say that you have to cook a dish. Okay, now there are two persons who are cooking the same dish, but they can follow different techniques to make this dish, right? So this way, the way you decode it or the way you design it, it tells the behavioral interpret of the design that how it's going to behave. So that is an overall, that's very high level abstract at how it's going to behave. Okay, but the kind of gates, the kind of flops you are going to use, that makes your netlist. Okay. Now, so you just understood the overall perspective of what is just synthesis, what's the primary input. This is not, I'm saying the complete input, but the primary input that you need for your synthesis process. Okay, now let's go deep drill down into it and understand, okay, but what are the different various inputs that are required for your synthesis process. Okay, so first, which I said, right, the first is the RTL code, which stands for register transfer logic. Okay, so as I said, that the functional behavior. Okay, I just said that I have to perform some function. Okay, I have to perform an adder, then a subtractor, then some multiplication. Okay, so this is something I just described in human format. Okay, I want to do this addition, I want to do this subtraction. This has to be described to the compiler. This has to be described or given in the form of a language that a compiler understands. Okay, so this is written in either Verilog or you can write it in VHDL, correct? So this is the main, or you can call this is the primary input which is being required. Okay, understand? For example, let's say you are, if I correlate to our normal to explain you, let's say for example, as I took an example, right? If you are preparing any dish, okay, and you're the main thing that is required to prepare a dish, for example, you're very unaware about how to make a dish, is you will buy a recipe book, correct? That's the main ingredient, because you have never cooked in your life, you don't know what's the process to follow. But the main input which is being required, it's your recipe book. Okay, it has like, you need to, for example, if you're making something, you're making, let's say, assume you're making pav bhaji. So it will take, okay, take this much potato, capsicum, take this much amount of this. Okay, so this is very upper language description, and this is called as your RTL code. Okay, now let's go down. Along with that, you need some other inputs. Okay, now let's come, which is SDC, which is like synopsis design constraint. It is stated as synopsis design constraint. It is not something that the cadence doesn't use it as an input or any other answers or there. It's a general perspective or general terminology which is called as SDCs. Okay, now I said, right, for example, that you are going to, just give me a moment, just give me a moment. Yeah, sorry, yeah. So SDC is correct. So now, for example, if you have a book, which I stated that you have a recipe book with yourself, okay. Now over there it is written, okay, that I have to like design this and this and this, okay. But there is something like, for example, if you are baking a cake, right, there has to be proper measurements, proper techniques that has to be followed to have a very good quality and fluffy cake, right? For example, something like you need to bake exactly for 20 minutes, let's say for 20 minutes, not for 30 minutes, correct? Okay. Why this is a kind of a constraint, right? In normal year life also, constraint is something that you're putting a restriction or you're giving a guidance, okay, that I want to bake it only for 20 minutes so that my cake will be fluffy, otherwise it won't be that as good as that I'm expecting. Similarly, there are a lot of different kind of constraints that are being given to the tool. Otherwise, you are just giving an RTL code and there is nothing like it will okay convert it into a form of different gates. But the main intention of the complete synthesis is just not converting your Verilog code to just in the form of gates. It has to do a lot of optimization. And the main thing that you need to do for optimization is constraining it through different constraints. Like if you have heard about the terminology in industry standard, it is called as PPA optimization. Okay, power, performance. Performance is nothing but your timing. How fast is your timing or something? Power, performance. So that is something that has to be provided to the tool for the guidance. And the next thing that is needed is your libraries. Okay. Now, there can be different, there are different, specifically when you broaden it to different two categories, it is called as a timing libraries and it is called as a physical libraries. Okay. The timing libraries, normally it's form of .lib you say, but when you use in the industry standard, you have to do a lib to db conversion because it understands in the form of .db file. Okay. And the physical libraries are in the format of the extension .lib. Okay. So when you now have to correlate it with our, because we are making a recipe, right? Now let me correlate it as, this is a kind of, for example, when you started preparing a dish, right? There can be lot of, for example, you're making pav bhaji as I stated. There can be a lot of ingredients which are available in the pantry, right? For example, there can be different, like you have masala from different vendors. There can be catch masala, Everest masala, blah, blah, blah. There are a lot of different masala types. But for example, if you are aware, like, okay, the Everest masala is very strong and I need my pav bhaji to be strong. Okay, I'm preparing it for someone who likes a stronger flavor or a bit spicy flavor. So what you do is, instead of having another masala which is of less strong, let's say catch masala is not that much strong. So that from the pantry, when you're selecting this kind of ingredients, okay, so make your dish as per your requirement. The same goes in this industry. Okay, in the library there can be different variety forms of various AND gates. Okay, let's say just take a simple AND gate or gate. Okay, basic gates I'm taking upon. For example, there can be an AND gate of different drive strengths. Okay, a drive strength is like as you go higher the drive strength, it will be like your device will be very faster. Okay, but since you're increasing the drive strength, you're increasing the area of your cell. Okay, so now depending upon this constraints also, right? As I said, if for example, if you're preparing a pav bhaji for someone who is a spicy lover, you'll take some stronger masalas. But for example, if your requirement is no, I have to make this dish for some a smaller kid who is just of 15 years old and he doesn't like spicy, he like a neutral flavor. So I won't put a lot of spices in it. Okay. So depending upon this constraints, the tool which is like your design compiler or your fusion compiler, it depends and selects like which flavor or which form of gate I have to use. Okay. It can be based upon various different drive strength. It can be in the form of, for example, there are different VT flavors of design which has been available. Okay. If I want my design to be low leaky or I want it to be very faster. So depending upon this, it will go in different kind of libraries and select it. So the timing libraries have a different as we go ahead, I'll explain you what are the different contents which are present in the timing libraries and what are the contents of the physical libraries. Along with this, you can also consider that one of the left, which is in the form of tech left, which we call it a .tech left file, which is technology left. Okay, which is being provided by your foundry. Okay, and this lib is also being this libraries is also being provided from your foundry or fabrication units end. Okay, not in the form of foundries, it can be from the vendors which are designing the standard cell. For example, if you're taking it from TSMC, it can be from them. From if you're taking the things from the synopsis, it can be from their end. Now this tech lab has to be definitely provided from the one which is fabrication unit. Okay, because the contents of this tech lab, it includes what kind of, for example, if you had heard about C, when you're considering that the data is being transferred through your logic. Okay, so it transfers from your AND gate to a flop, then from a flop to a memory. Okay, it goes through wires. This is not the physical wires that are present in our house. Okay, it is in the form of metal layers. Metal layer wires are there. Okay, so each foundry, whenever you go in a different node or different, they have a different metal stack layers. It can be 13 metal layer, 19 metal layer. So this information has to be also provided, right? That man, for example, I only have 10 metal layer stacks. Okay, so I have to design it in this way that my design should be routable within this 10 metal stack layers. Okay, so this information is being provided through the tech-lab file, which gives what are the kind of layers I have in my design, what are the kind of VRs. Okay, VR
Ma'am, excuse me, ma'am. Ma'am, do we specify the drive strengths of the cells to be used in the synthesis, ma'am?
synthesis, we gave it in the form of library, right? Once the library have it, now your optimization engine is working in it. Okay, now optimization engine got to know that, for example, if I swap my two drive and 2D and 2D, I'm saying two drive strength to 3D. Okay, now it understood that I can upsize it, but now it will go in the library and search, do I have a 3 drive strength cells? If the library doesn't have it, it can't do. Because for example, if you want to go in your pantry and then masala itself is not there, how can you do it? Even if you know that if this masala would have been there, I could have optimized it better. Okay, but since
Okay.
your masala is not there, how can you do it?
Okay, it adjusts with the thing which is available.
Yeah. So see, optimize. There is a see. I'm. This is just the starting of the process. When optimization is engine is working through it, right? It needs to understand that okay, if this path is not being met, okay. Now, for example, I can upsize the drive strength. Okay, now it's saying that okay, I have 2 drive strength cell which is currently there. Let me look in the library if there is a 3 drive strength cells available. Okay, and it find that no, 3 drive strength cell is not available. Then what it can do is it can again go and search in the libraries. Okay, do I have a low VT flavor of my design? Okay, because low VT is faster cell, because my timing is setup is being degraded. Let me try it swapping with the low VT flavor. So okay, I see. Okay, I have a low VT flavor in the design, and now I can swap it. Okay, now the
Yeah, ma'am.
advantage of swapping with VT is that your footprints remain the same. There is no changes in your size of the cell. Okay, but something you can't specifically see. You can guide the tools to a lot of constraint that kindly don't use to. You can give it through don't touch cell list. These are the kind of constraints you can give it. But when you're doing a synthesis, you are not allowed to restrict a lot of things at the synthesis end. You can restrict it at the PNR end based on your like project to project experience. You get it like okay, this cell is not useful for my design. It is not helping me out through my optimization, so I can restrict it by passing on like don't touch or don't use. Okay, but as of now when you're doing a synthesis, you cannot put a very hardcore constraint that I cannot use the cells, and whatever cells that you can use are present in the libraries.
Okay, ma'am.
Okay.
Okay. And one more, if possible, explain now or in the future, ma'am, that is the difference between the tech left and the technology file.
Yeah, we'll have a very dedicated lecture by explaining like in depth about what is complete RTL, what are the contents of RTL, how is an SDC is being written, what does the timing library contains, how what all are the contents of TechLef as well. I'll explain you
Okay,
through
ma'am.
your this lab session as well. We'll try to open up and go through it one by one.
Okay, ma'am. Sure, ma'am. Thank you.
Okay. So
Okay, ma'am.
yeah. Okay. So now we were like, as I said, like TechLef is something like that is also a mandatory file because see, if you are preparing addition with each other, as we are going with the example, correct? So now, for example, it is a kind of thing like, for example, what kind of rolling pin I have to use, what kind of rolling board I have to use, kind of strainer, pan, because that is only the thing which is available in the kitchen. I have to use it. So when I'm going to the foundry telling that this is my design, the foundry would state it that, oh, have you used only those materials which I gave it to you or not? Correct? If you're not using it, then the foundry cannot fabricate it, because they also have some guidelines, some rules, constraints being defined at their end. Okay. So finally, we understood that these are the kind of major inputs that are being required for doing synthesis. The first is your RTL, which is being written in your Verilog and VHDL. Second is your design constraints file, which have a lot of constraints related to timing, area, and power. And then also major bucket of your libraries, which can be your timing libraries, physical libraries, and your technology libraries, which is in your TechLib file. Now, let's look at what are the different kind of outputs that is being generated by this flow. Okay, as I stated, right, the first and the primary goal of the synthesis is to generate the net list. Okay, if you just cut down it, it just gave you net and the list. It is like the network formed between your cells is called as net list. Okay, it will have what are the different kind of gates, standard gates, like your say combinational logic gates, your sequential logic gates. Okay, and with and what is your connectivity through them, what are the wires. Okay, so this is a kind of a language that is being understand by the machine. Okay, so the first primary output is nothing but your gate level netlist. Okay, then once this is not a kind of output, but this is kind of once the process goes through, right, that is your complete synthesis process, it will have something which is called as log, which is as an engineer, as the great engineers are the one. For example, what happens like when you're doing a process in the flow in a real life world in the industries, right? The process, see, the design that you have in college is hardly of, let's say, of even 100 instance count or 2000 instance count. But when industry works, it's in millions and billions. This process that when it goes through, right, it takes a lot of amount of time. The higher the complexity of design, the longer the duration it takes. So it might take 2 hours, 3 hours for a process to continue. So the output will be definitely dumped when the process is done. But meanwhile, this there is a file which is called as log. Okay, this keeps on ongoing as and when your process is done. The the smartest engineers are the one who goes and check in the log that what is happening, and the one which I am telling the tool and the what is my intention, it is doing it the right way or not. Okay, for example, if you're at mostly in an industry, the routing is the stage which take around days and days for the complex design. It has a runtime of around more than 48 hours. Okay, now why, for example, if you're an engineer and you're saying that my routing is going on for more than 3 days, the smartest engineer, what it will do, it will open up the log and see, okay, am I seeing the congestion issues. It will go and see what are the grcs, how much overflow I am having. Okay, because anyways the output will be dumped when the process is done. But if you are waiting for the process to be done, it will take a lot of time. So something that you can do a manual intervention is to open up the log and check up whether the tool is doing the intended things or not. And the next thing, which is being dumped after your complete process is done, that is main intended is to look for are your different kind of reports. Okay. Now, the main intention of this SDC file, as I stated, right, was to constrain your design, like how should be my timing, how should be my power, how should be my area. Okay. Now, the main intention is met or not will be available only when you do the reportings. Okay, so there are different kind of reportings which are being available. There are some standard which are being standard files which are being dumped by the flow. Not, they are not automatically dumped. You have to make the tool understand that I need, you have to give it as report timing, report underscore area, report power. But there are something that, since the industry standard is very huge, they are not following only this thing. They make a wrapper around it and they do a lot of scripting and find it out. Like, you cannot go manually through each of them report. Okay, so the main report that every engineers look for is, in industry standard, it is called as QOR report. Okay, QOR stands for quality of result. Okay, so it is a kind of You can say QR report is a kind of a summary report. It has all, for example, at the first section, it will have how many instances are there in your design, how many combinational, how many sequential, okay. Then how is your timing been met? It will give you a global timing report kind of a thing. Then what's the area of the total combinational sense in your design, so that you get an initial understanding or initial just okay. After this, I have done the synthesis. I am in this shape, because a lot of process has to be done even by the PNR folks, right? At the initial itself, for example, I just looked at, I have an area target, and now when I'm looking at it, right, I'm seeing that I am going out of my area budget, or something like I have this much requirement of power, but I'm going out of my power requirement. So something that you need to tally it, because you have a budget, you have that okay, this is my requirement, and whether I'm meeting it or not. Okay, so this is very, very overall high level I have given you, like in explaining in a very simple format, like what is actually being the primary inputs and what are the different primary outputs which are being required for performing your synthesis. Okay. Now, I'll just give a summary of what are the basic inputs and outputs which are being required by the synthesis. I just want you guys to tell me what about the basic inputs? Any of the participants, unmute and tell me. We will just have a water break.
These inputs are RTL, dot SDC, and timing as well as physical libraries. And outputs are gate level netlist, log file, as well as the reports for various like timing, power area.
Correct. Guys, you all are there, right? Or is it the one person who is attending my session? I want all of you to be awake, right? Okay. So, the different kind of inputs are, as I stated, RTL, which is register transfer logic, which is written in the format of either Verilog or VHDL. Then there are different kind of libraries, physical libraries, timing libraries, and techlabs. And there is something which is called as your SDC's constraints. Okay. And the primary output that is being generated, okay. So that is your gate level netlist, the different reports which are being dumped, and what are your different kind of logs. Okay. Now let's moving ahead. Okay. Just give me a moment. Just give me a moment.
Hi, madam. So one small doubt. So in UPF file, we are not required to in input file. Hello.
Okay. So there are different ways of synthesis. Okay. There are two synthesis. One is
Okay.
called log. Hello.
Sorry. Yes, yes. Please tell me.
Yeah. So there are two different kind of synthesis method. One is normally called as logic aware synthesis, and
Okay.
second is physical aware synthesis. And
Okay.
third one, which require a UPF, is called as power aware synthesis. Okay.
Okay.
Nowadays, technology is trending is something that you can see. Your RTL will never have an intent of your power, correct?
Yes.
It
Yes.
only has okay, I need to perform this is the action, okay. But in case you're performing a power aware synthesis, you need
Okay.
to define, or you need to tell the tool, okay, these are, I am performing a power aware synthesis. I have a notion that I'll have, for example, my design will be on 3 different power domains. Okay.
Okay.
One of the power domain will be always on, one of the power domain is switchable. Okay. So then, yeah, you have to consider UPF as well while performing a physical aware synthesis.
Okay.
Excuse me, ma'am. What about the Scandef, ma'am?
See, scanned, you understand what is actually a Scandef is? Can you just explain me what is Scandef?
Yeah, for the inbuilt testing of the flops, we insert some Scandef files so that it itself tests the whether flops are working well or not.
Okay. So whether the flops are working well or not. So how do you test, how do you convert, or how do you make a design understandable that it can be converted to a testable flops?
Yeah.
Hello?
Ma'am.
You're aware about how does a tool do? Or what does a scan team does?
Yeah, they 80 PG automatic test pattern generator. They give that and they.
So this is a kind of a testing you do at a final end that at the scan team does it, right? They pass on a different patterns to check whether your design, whether it has a different kind of faults, like stuck at 0 fault, stuck at 1 fault. There are different kind of a test which is being done. How much is your test coverage? They
Yes.
generate this. Okay.
Okay, ma'am.
But see, the thing is, for example, one is see different industry standard formats follows different formats. Something they have is one team can do it synthesis, one team will do it as a part of synthesis, pass it on to a DFT team. Okay, DFT stands for design for testability. Okay,
Okay.
okay. There are few organizations who can do it in merge format. Okay, they can do synthesis and DFT together. Okay, they can inculcate DFT along with the synthesis. So Scandef is something what happens it, right? For def is a, you know what's the acronym of def? Def stands for design exchange format. Anything which has an information about kind of where will my this, for example, where will your this flop sit in your design, what will be the location of your AND gate, where is this sitting, how is my tracks being defined. Okay, so the way it's kind of a placement of different various components of your design is nothing but your def. Now Scandef, this Scandef is something, see, in order to make your design testable, okay, see, AND or gate, all of this can be tested, but something which is very the which is not in too much quick to test is your sequential cells, especially your flop latches. Okay, because they are also dependent upon the clock, and you don't know what is its already previous state, right? There are different states of your this. Okay, you could have set it to clear logic, or you could have provided an asynchronous input. Okay, so you are not aware about what was the previous states of this logic. So in order to make this flops specially testable, you convert this normal flop to something which is called as a scannable flop.
Yeah, ma'am.
If you go in normal industry standard and look at this naming convention, a DFF is converted to SDFF. Okay, scannable D flip flops. It is nothing but you kind of attaching a mux along with it.
Yeah.
Okay, and the select line decides whether you are in. See, there are different. If you go, I have to explain various different concepts like the different modes. Mcmm also you would have heard. Okay, what are the different modes in your design? There is a mode like either you are in a functional mode. Very brief. If I have to give two modes, there is functional mode and there is a scannable scan mode or debug mode. It is normally called as. Okay, when a chip is being designed and fabricated and everything is done and it is outside into the market, okay, it will never ever work in scannable or your debug mode. This is something for your understanding, or when before you release out this chip to the market. Okay,
Yeah, ma'am.
okay, for example, I'll give you very layman language description. Now we were cooking a food, this process of synthesis I correlated with you and you made a dish. Okay, now what happens? For example, you are a chef, you're a lower level chef in a very hi-fi restaurant. Okay, now once you're making this design, okay, you're making this dish. Now that's your primary responsibilities that you need to take it to your head chef, okay, senior chef, and make them like, can you just taste it whether I have made it in a proper way or not, correct? Because if you don't take it to the head chef, maybe sometimes like your salt is not proper, or sometimes it's not properly cooked as it is expected, right? And now if it goes out to the person who is sitting in your restaurant or your hotel, right, may give you feedback with a lot of complaints, right? And now let us assume that you made this dish for 100 folks, and before taking it to your head chef or to your senior level chef, you didn't ask them to test it. Test it means this is taste, okay? TASTE, taste, not test, okay? You didn't take to them. Now you have prepared it in this much quantity, and now the head chef tells you this is not properly cooked. This is undercooked. You need to cook it for 3 more minutes. And the way it's kind of a bit more salty, just squeeze a lemon so that it comes out. Okay, now this is the response that you got from the head chef, but let us assume that you already distributed these things to the to the persons who are sitting in your restaurant. Now see, 100 folks will come up and say that no man, your dish is not good, your dish is not proper, right? So similarly happens in the VLSI field as well. When you are about to manufacture it in the market, right? This is something that this RTL to GDS is something this is being done at our end. Once this design and being is completed, right? They also need to done a lot of testing. Okay, so in order to make them testable, these are the kind of units we implemented from our end itself. So that is why that so that they can test it. Okay, so now what happens is in front of this normal flip-flops, right? They will attach a mux, right? 2x1 mux. You understand the functionality of mux, right? For example, if your select line is 0, it selects whatever is your first input and passes it on. If your select line is 1, it will select what is the next input. So what happens is, for example, as I said, right, there are two primary modes in which our chip works. One is the functional mode and second is the debug mode. Okay. If you are working in the functional mode, the select input will be 0, let's say. So it's like normal functionality of chip. Now, once you have designed the chip and it goes to the validation folks. So what they do is like then they will use this series of 101011. These are the different automatic patterns which are being generated. Okay, and you will pass it on through this mux. Okay, and these
You're
are called
showing something?
scannable.
You are showing something?
No. I don't have the this
You
scannable
can draw it
flops.
using pen also. You can draw it if you want. That is fine.
Okay, so let us assume, see, you had your normal flops in your design. Okay, now in order to make it scannable flop, what you did is you attach an extra logic which is of called as mux. Okay, so let us assume that SE normally this is an industry standard, like a lot of SDFFs like scannable flop have pins like SI, SE. Okay,
I'm sorry, you're not audible, ma'am.
redraw it again. Just give me a second.
Your voice is not coming.
Hello.
Yeah. Increase the voice also. Increase the voice also.
Yeah, voice is completely expanded.
You are using a like web based or you have downloaded the Zoom because a lot of noise is coming. If you can download the Zoom and then join, then there will be no new noise
This
actually.
is
Right
through
now,
application. It's through application itself. It's not web
okay,
browser.
this is application. Okay, then it is fine.
Yeah.
Okay, fine. Yeah, you can continue.
Okay. So as I was stating, right? See, when your normal flops are there, they cannot be tested simply because they have a previous modes. Okay, you do have something which is called as asynchronous pins, which is asynchronous preset and asynchronous clear. Okay, so in order to test your flip flops, they have a concept of scannable flops. Okay, so scannable flop is nothing but along with your normal flops, it it has an additional multiplexer, 2x1 multiplexers. So one of the primary input of this multiplexer is your data logic, which has to be used in your functional mode. And the other is something which is called as your scannable input, which is nothing but your list of series of ones and zeros combination, which is being generated by your ATPG. So once this is goes in for your validation, right? When they are validating whether your flops are how are they in the perfect condition. There are different kind of checks which are being done by DFT. I'm not completely aware about a lot of checks, but yeah, stuck at 0, stuck at 1. There are different kinds of things which is being done from DFT team. They look at the how's your test coverages, okay? Because it's not really possible to convert all the flops into scannable flops, right? Because there are disadvantage. For example, if you look at it, right, ahead of every flops you have this mux been attached, so your area increases, okay? So they have the percentage requirement that majority of the flops we will try to convert it, and we think which are not of that much use, we'll keep it as a normal flop. So when they are doing a validation from their end, that whether they are testing how are the flops been working, they are making always scan in pin. For example, let's say that the scan in pin is always enabled. Okay, so now what happens is there the inputs comes through the scannable input and it goes, there is a scan chain. Okay, this is not simple. There is lot of such things that it goes through such different flops. For example, if in the design, let us say if there are 1,000, let me consider if there are 1,000 flops in your design and they have a target like at least 50% will have a test coverage. So they will convert at least 500 flops to the scannable flops. Okay. And thus this scannable flops are then converted back to back in the form of a chain. That is why they are called a scan chain. Okay. So this scan chain insertion, this scan chain information is provided also from the DFT team. Okay, that this is the way that my scan information will flow. So keep this flop connected in this way. Okay, so this information is then provided in the form of a def. So that is something some industry format can, along with the synthesis, can use it, that they have a tie up with this DFT folks and they'll ask for the Scandef, but that's not something which is primary input. I was just discussing about what's the very much important core primary input that are being required. If you're doing a power aware synthesis, yes, you need a UPF. If you are doing, I'm saying physical aware synthesis. What does a physical aware synthesis means, right? See, at synthesis, I am not sure what a PNR guy is. PNR stands for place and route, or you call it as a PD engineer. Okay, I'm not sure like what is the kind of floor plan he will have. Whether he will be using a squarish floor plan, rectangular floor plan, where will be the notch in the design. So at synthesis, it's not, earlier back then they were not completely aware like what kind of floor plan is being going to be used. So as and when the technology upgraded and they decided that let's make synthesis also physical aware, that okay, let's have a dummy trial with finalized floor plan. Okay, but it never happens in the industry that whatever def that synthesis team has followed, it is mandatory that the PNR folk will also follow. But yes, you can give a rough estimate in the form of a def. Okay, so then you have to give a def for your physical aware synthesis. For power aware, you will give a UPF. And in case, for example, you're merging up with your DFT team, then there is something that they will ask you for this Scandef. Okay, so this Scandef, initially they would have given you on the early basis, they will give you the list of flop that has to be just interconnected. What happens is when the synthesis goes in complete detail analysis, you will, there is a step which happens in synthesis which is called a scan chain reordering. Okay, so what happens is, okay, for example, let's say this is your complete,
You are drawing something?
is it, the box is not visible?
Yeah, box is visible. Do the full screen also.
Pardon?
Do the full screen, full screen.
Box.
It is showing me PPT actually. It is showing me PPT.
Oh, is it showing?
Slide number 4. Box is not visible.
Let me know once it's up.
Yeah, now it is visible. Now it is fine.
Okay, fine. See, let's say for example, when initially you had no notion where your flops are going to be placed, right? Because your synthesis at right now you're at synthesis stage, not at, let's say, PNR stage. Okay, for example, I'm very high level, I'm giving you what happens with this thing. Okay, these inner boxes, let's say like these are all flops. Okay, now scan team gave you the connectivity in the form of a def. Okay, let me say 1 and giving the number 3. Okay, now they gave you a connectivity that okay, my scan input will come out from this, it will go and then come to this, because they were not sure how is the placement of your flops, right? This way Let us say this will go to this will come, and this will then go to this, and this will go to this. So what happens when you're doing at your synthesis stage, you can enable something which is called a scan chain reordering. Okay, see what happens is there is no, see if you look at it functionality wise, scan chain thing can still detect whether all the flops are working in the proper condition or not. But what happens, see, you are going to design it, and the way these lines which I have been drawn, right, they are nothing but your wires in your silicon chip, right? And now for example, what happens if you're having longer wires routes, you're using the resources that are not being intended, right? The longer the routes, the more will be your delay. Okay, it will cause a congestion in this issue, congestion in this area, correct? So what happens is in this scan chain ordering, right, let's say you say same this kind of a thing. I'm not altering the location of the flops. Okay, I'm saying because this flop I have intended to keep it like this because I have to meet my functionality. See, if you talk about two modes, which is functional mode and the scannable or debug mode, the main intent of the design is to meet the functionality. Scan is a mode just to test whether the chip is functional properly or not. So the priority is given to the functional mode. So on this functional mode, when I checked it, I understood, yes, my design works very properly when I have the flop placement in same manner. Okay, so I don't want to alter this flop. Okay, because this, maybe this flop which I over here, it communicates with some ports or some logic which is sitting over here. So I don't want to alter it. Okay, so now what I will do is in the scan chain ordering, like I just want to have the check whether these flops are working fine or not. So instead of my one, okay, instead of this going directly to 4, what I will state, okay, let the logic pass and go to flop 2, because this is nothing. See, there is no logical, it doesn't go through logic cloud, okay, that it has to be transformed. If you are passing over here one, the one should come over here, the one should come over here, and from all the things it should finally one should only come at the output. There is no combination logic cloud which is present between these flops. This is present only in your functional mode, not in your scannable or debug mode. Okay, then I say, okay, let this whatever logic is coming for scan, let it go through one, flop number two, flop number three, then let it go to flop number six, flop number five, flop number four. Okay, and then in the physical world, there is something which is called as a test probe. Okay, that's very high level language, that okay, out of this then you will tap at this and you will collect, okay, at what are the inputs which are being coming. So see, I have saved on a lot of my resources, correct? This resources will help me to avoid congestion. Even it will help me to increase my area availability for placing the different kind of other cells. So this is something, this once this I have designed that this scan chain reordering is done, then again I'll dump a def which is called as a Scandef. This is not matching with whatever primary Scandef that is being provided by the DFT team, because I have reordered my scan chain logic, and then this def has to go through because you have to inform now to the DFT team. So you will give this Scandef as an input now, your modified Scandef to your DFT team, that man, now the flop logic connectivity is not 1 to 4, 4 to 2, 2 to 3, 3 to 5, 5 to 6. It has now changed, and now the way it is being connected is 1, 2, 3, 6, 5, 4. And this information is present in your form of Scandef. Okay. Did it answer your logic? Did I answer your question?
Yeah, ma'am. Yeah, ma'am.
Yeah.
Hello, ma'am. Excuse me, ma'am.
Hello.
Hello, ma'am. Excuse me, ma'am. Am I audible to you?
Yeah.
Yes.
Ma'am, you said output of synthesis files are netlist file and reports and log. And what about remaining outputs like generated SDC and DDF files?
Pardon.
I mean, remaining output files like generated SDC and DDF files.
TDF. I didn't get.
I mean generated SDC, ma'am. SDC file output.
Yeah. See, at the end, see this SDC's file, you can say it can be a form of generated SDCs, but see, synthesis team will give you as a part of synthesis, right? You will have SDCs as an input. In case, for example, if you are making the changes from your end, which is not been allowed, but yeah, for example, it happened that you decided that you made a lot of progress in your design, and now at the very last stage you are saying that since I'm unable to close my design, let's say at higher frequency, let me bring it down to lower frequencies. Okay, then you can modify the SDCs and then you can pass it on to the next step, which is called as a PNR step. Okay, the generated SDCs will be almost equivalent to whatever is your input SDCs which is being provided. Okay,
Okay.
but neither of the time it changes. Very rarely in very hard project, for example, if all of the blocks in your particular unit is facing some issues and now you are still having a flexibility not to to change your clock, you are allowed to change it, but that's a very rarest case. It doesn't
But
happen in that way.
but finally we need to give it as input to the PNR for PNR number. PNR.
Yeah, so
Yeah.
that finally whatever the files you have generated, it will definitely go to the next step, which is your PNR folks. But the changes, if you look at the changes in the SDCs which are being provided at your end versus the one which goes to the PNR, have hardly, as I stated, right, in PNR what will happen is it will go through floor plan, it will go through your placement, CTS, routing, right? Now, for example, if you are very much sure that in your, it happens project to project wise, this I have looked at it, that for example, you have in the past 10 projects, you looked at it that these special kind of cells, if you are using it, it is not giving you any advantage in terms of timing, or it is a kind of a cell which is occupying large area and it is not helping you out. Okay, so that constraints can be provided to the PNR team, which I stated, like don't use. Don't use cells. Okay, there is something that, for example, it happens. For example, you have in the while doing the synthesis, they have generated some logic. It can happen that PNR folks can alter it. Okay, during their optimization, but you want that no. This logic should remain untouched. I don't want it, even if they're trying to optimize this. Don't touch this logic. You can put don't touch on it. So these are the different additional constraints along with your normal constraints. You have to provide it to your PNR folks. Okay, so this is kind of PNR constraints. Okay, that whether I should provide, I should use the cells or not, whether I should use it. There are different kind of CTS level constraints as well, right? That you have to provide it. Kindly use these kind of cell list. Okay, don't use this kind. Whenever you are building a clock, right, you're allowed to use only clock buffers or clock inverters because it has an advantage over the normal buffers. But the disadvantage is that their size is bigger. But you want like your timing to be met and it has a good clock, like it has good producing capacity of clock. So this is, see, constraints normally is nothing but guiding your tool on how to produce a design meeting your specifications, nothing else.
Can you give a small description about DDF file?
I'm not getting which is TDF. What is
DDF file.
DDF file?
Yes.
What does what's
And not DDC file, not DDF, DDC file.
is it .sdc file? That's I'm design constraints is SDC file. I'm not sure if any other terminologies that I have worked with. It's normally called .sdc files.
I mean,
This is design.
I came to know that in DDC file where you can get all things like generated SDC and Netlist, all the things are measured in this file. I came to know that.
It can be with respect to different maybe, but I know that the constraints have to be passed in .sdc's file. Okay, it can be zipped or something sdc.gz or something, but I'm not sure if any vendor specifically, because I'm not worked with Cadence tool. I've always worked with Synopsys tools.
Yeah, actually while doing a project in synthesis, I mean in a Synopsys tool only, we also dump this DDC file.
Okay, so,
Netlist file along with generated SDC, and we also read about DDC file.
and what are the contents of .ddc file?
Actually, I did not go into that file, but I came to know from others where we can contain the information, material information like Netlist, generate SDC. This information you will get. I came to know that.
I just go through it because I've never gone through .ddc file. I've always looked at SDCs. It can be something like the way your flow has been designed. It is something, it is like, it has a zip version of all the outputs which are being dumped by synthesis and kept at one place. It
Yes,
can
yes.
be like this because you are stating like it has constraint, it has netlist, it has everything. So it might be like it is a flow that has been designed to dump it in that manner. Okay, I'll just get back. I'll go through it, and if there is something called as .ddc, and check and get back to you in the next lecture.
Right.
Okay. Fine. Then, so now, see, uh, as I stated, right, there is a complete this process which is called as synthesis, right? You understood what are the inputs. You understand what are the different kind of outputs, right? Now what happens is you understood what are the ingredients that you have to take. Okay. Now the process is something that the chef has to perform it. Okay. And now you understood that the output is a dish which is meeting the taste, it is good in flavors, it is properly cooked, which is like whatever the constraints you provided it, it is meeting and has the output as primarily as netlist. Okay. But this process which happened during this, right? Whatever your chef did it has to correlate with whatever happens in the synthesis. Okay. So an overall view about how does the synthesis works, right? The first level, what is done is you would have heard that it is called as synthesis is called as storm model, okay, which is nothing but translation, optimization, and mapping. Okay. So when we talk about the term as translation, okay, now very familiar word translate is to convert. Translate is nothing but to convert from one form to another form. Okay. Now translate. See, at the synthesis, you understood what is the input, which is your RTL. RTL is written in Verilog and HDL. Okay. Now we are moving ahead, making this RTL code into different language, which is called as nothing but your netlist language. Okay. So it has to be converted in the form of gates. Okay. Or it's kind of a Boolean representation in over here, right? For example, when I stated, when I'm correlating with the recipe itself, let me give you an example. Like, for example, you have a recipe book with you. Okay. And it's this recipe is this recipe book is written by your grandma. Okay. Now in grandma, when you write this recipe, she would have written add a pinch of magic. This is the way she wrote this book. Now, as a part of synthesis engineer or as a part of chef, you have to understand that add a pinch of magic means nothing but you have to add some salt. Okay. Now you have to understand that you have to add at least 10 gram of salt in your dish to make it taste proper. So similarly, here also you are converting your Verilog or VHDL, which is your RTL code, into form of Boolean expression. Okay, I have took it in a very simple example for your understanding that, for example, if you would have written your RTL code for an AND gate, right? You have something that assign y is equals to a and b. Okay, this is an ampersand which is being met. But when it translates to a Boolean logic, okay, there are a lot. See, this is very simple example, but when you go in a real world example, there will be a lot of complex examples. Okay, so the tool has to understand and depict it out of this that which kind of logic, which kind of a gate or what flop or what I have to use it for it. So the first step that it does is it just translate your RTL code into this kind of a Boolean form, which is nothing but your, for example, dot. I hope you're aware that dot is a representation of an AND gate, plus is a symbol of your OR gate. Okay. So it just simply like out of your complete, there will be no assign statement in your netlist. Okay. It will just say that Y, which is your output, is nothing but A and B. Okay. I have mentioned in the highlight there is no optimization yet, right? It's just a logic. Okay. Now Once you have this raw logic being ready, okay, there comes then the main primary importance of synthesis is optimization. See, it was very easy if there was no optimization. I would have just got the RTL and just converted into all the random gates looking at very simplified way. Okay, but the main intention of complete synthesis is optimization, and to perform this optimization you have this constraints file, right? Because you don't know how much to optimize, correct? This optimization guidelines has been provided through your SDC. Man, this is the path, it has to be met through this and this is my power budget. You can't use the cells which are very high leaky because this is being designed for my logic which has this budget. Okay, you can't go beyond this area because I have only this much core area available for my logic. Okay, so then comes this picture of optimization. So while doing this optimization, the tool will have to look what are the SDCs that are you have been provided. Along with it, for example, when you're optimizing it, what are the cells which are available in my libraries? Okay, so next is nothing but your logic optimization. Okay, and the optimization in purely industry standard, you will always say it as PPA. Okay, timing, power, and area. Okay, so for example, if you want to optimize your area, you can use the cells with lower area, right? For example, if you are there is an operation which has to be performed, for example, three three A and B and C has to be done. Okay, there is a flexibility that for what I can do is, for example, see, I'm saying okay, or let's say what's the whatever is the example I have mentioned it over here, right? If you look at A and B or A and B bar, see, if you have remember your digital electronics, right? For example, if I do it through A and B, okay, and then I have put it as that is a symbol, the pipeline is a symbol for OR gate, and A dot B bar. Okay, now you know that since there are two similar logics A and B and A and B bar, I can take A out. Okay, now say A. Okay, now what remains is B plus B bar. What is B plus B bar? Then what is B plus B bar? What will it results to?
1, ma'am. Logic 1.
Logic 1, because if B is 0, B bar will be 1. If B is 1, B bar will be 0. So anytime an OR if you do between 1 and 0, it will always result into 1. Okay, so this will be A dot 1. And if you have an AND with 1, what is the output always? Guys, very basic digital electronics. A and 1 will give you
A.
A only.
A, correct? Because if A is 0, 0 and 1 will make 0. If A is 1, 1 and 1 will give you 1. Okay, so now there is nothing with A. So see, this is very simple Boolean logic optimization that I have done. There are, as we go ahead, I'll explain, there are different kind of optimization strategies which is being used by the tools, right? Because the complexity of the logic in the real world is very high. So it has to do a lot of optimization technique. So now instead of me using I would have used A and B, one AND gate, one OR gate, and then again one AND gate, right? Three gates. There is nothing but I would have just simplified it and just taken the input as A. So this is a kind of different optimization that the tool has to do it in order to understand it. So this optimization techniques also you guide it through the tools, right? That okay, I have to do this kind of boundary optimizations. There is retiming. I need to enable it. Okay, I want to do it through group. I'll explain you as we go from it. A lot of different optimization techniques that are has to be present so that the tool understands. Okay, how can I save on power? How can I save on area? So this is the way the tool understands and generates your logic. So this is where the complete synthesis revolve around, which is your nothing but your optimization. Okay. And then comes something which is the third step. Where are we? Okay. So then there is a way which is called as technology mapping. Okay. See, what happens is when you were developing an RTL code, right? The RTL, the person who is writing this RTL code has nothing to do with what tech node which you are going to use. Okay, if you go in tech node, this is a very complete vast topic. I'm not going to touch into it. You can, if you're very much interested, like how does this tech node has evolved from 180 nanometer to right currently we are in 3 nanometer, 1.8 18 angstrom, which is by Intel, 2 nanometer by TSMC. So the RTL person is the least caring person. He's like, the specification is achieved to me, I will just write it in the form of a code. Okay, and that is, he's completely in, he doesn't know like from which node is the cells going to be being used. Okay, so now in order to make it, to understand it, right, because fabrication units like the foundry or the fab with either TSMC or through Samsung, whatever you're going to Intel, they need to understand, they have different kind of techniques for different technos, right? So they need to understand that you have used which kind of thing. So now what happens is, the Boolean logic that you have, for example, you have been designed, right? How will it go and to which cell it will map, right? I just said that, for example, there can be, like for AND gate itself, there can be various flavors. If you guys would have anytime opened up the library, right? Across the library, even across the different corners, you don't have library just like as library. These libraries will be present across various corners in your design. Your SSG, FFG corner, typical corner, your different PVT. That's all in all very different vast topic. I'll explain you as we go further. But yeah, so you have to understand, for example, this gate which I'm using is of which drive strength, which VT flavor. Okay, so this is how you're mapping, because you can't simply write down and. Okay, that is for your understanding, that you are understanding, okay, this will be done using AND gate. But what AND gate has to be explained, right? So there comes your mapping. You are saying that please, this cell has to be mapped to this library cell. Okay, this is where the picture of complete, I said, overall view of what a synthesis done is called as TOM model. TOM stands for translation, optimization, and the final step is your mapping. Okay, so in translation, you convert whatever is your higher level language written in your Verilog or VHDL and convert it to a very simplified Boolean logic. Once this Boolean logic is done, available, then the tool starts an optimization into it. There are around more than 5 to 6 very famous optimization techniques which has been used by the compiler, DC compiler or FC. Okay, we'll go in that in detail. And finally, is like you have to map your cells to which cell you are going to use, to which technology out of this library, whether I'm going to use AND LVT or am I going to use AND HVT, which is low VT or high VT, or which drive strengths, so that the finally it comes to know, okay, this is the kind of cell I am going to use.
Ma'am,
Okay.
excuse me.
Yeah.
Ma'am, why don't we dump the MMC file for the synthesis, ma'am?
Pardon?
Why don't we give?
I said libraries have to be given in the form of different MMC, right? That is not .1.lib file. If you look at, if you would have done your project and if you look at .lib file, right? You have to give this .lib file for MMCC, all the multi-corners mode, correct? It has to be, if you look at, because see, in when this library which is being made by, this is made by some standard cell library characterization team. Okay, they do this. This is a complete entire ballpark different game, that how do they do this, how do they design it, how do they know it. Okay, so for example, if an AND gate is under this much voltage, how will this AND gate behave, right? If it is under higher voltage, it will generate the output faster. Okay, because higher your voltage, it will be faster in the speed. Okay, lower the delay. So this library that you are being providing are your kind of different modes, different corners. There will be, for I'm not sure if you would have, have you ever done the project and have you included the library just for one, or you're using it for all the various corners that are available in your design, different PVT corners?
Usually
Maybe
for all corners.
Yeah, for all the corners.
Hello.
Maybe it has all the corner
Yes.
info in it.
Yeah, so that's what I'm saying, right? The main what you call as PVT, right? PVT stands for process, voltage, and temperature. When you talk about the processes, right? Typically there are industry standard formats follow three different types of process, right? It says SS, which is slow, okay. Then it says TT, which is typical, and third is FF, which is fast. This is nothing but because your CMOS, see, entire thing is built using CMOS, and CMOS has two different kind of stuff, which is called as PMOS and an
Yeah,
NMOS. Hello.
yeah, ma'am. I'm just adding the thing which are just saying.
Yeah.
It has PMOS and NMOS. One is fast and other could be fast or slow.
Yeah, so this characterization they're done. For example, if this is both of them are slow, how will my design respond? Okay, if they both are fast, how will my design respond? What could be the delay? Okay, then comes every MCMM is made up of your this. See, I just at the initial I gave you different mode in which the design works. Okay, very broad specifically I stated two modes. One is your functional mode and second is your scan or shift, or you can call it as a debug mode. Okay, along with this, when you combine it with the different PVTs, okay, this becomes your corners. What is the voltage? See, if you have something, same design is operated on, let's say 0.6 volt, and some same design is operated on 0.67 volt, because you don't know exactly. See, what happens when you look at a very bigger picture, it can happen that there will be a lot of IR drops, okay, in your design. It may happen that the design was intended, that this cell was intended to receive, let's say 0.67 volt, okay. But since there was a lot of drops, that drops can be due to a lot of issues, whether there were high density cell occupying, they were switching at the same time, or was it due to, for example, the resistance, the metal layers was used was on lower layers. A lot of that's complete different theory subject. So, but for example, let's say that instead of 0.67 volt, it got 0.6 volt. Now what happens is, for example, this is VDD, okay? If your VDD is reducing, the delay of the cell will increase. If you look at the graph, okay? Let me okay, let's say this is your voltage. This is your, let's say, I'm giving it as a tau, which is in industry standard, it is something which is delay, okay? As your voltage will increase, what will happen? Your delay will decrease. Okay, but now, as of now, for example, I stated, right? Your voltage has moved from 0.67 to 0.6 because of IR drop. So what happens that your cell delay has increased. Okay, now what happens when if you have the two axes and you're doing a project, right? When you go do a report timing, same path, you take exactly the same path, but check your path and report it in two different corners. One you take and report it in 0.67 corner, okay, and one you take and report it in 0.6 corner. Exactly the same cell, same path, it should be there, same start point, same end point, and go through logic should also be same. Now, if you look at two different corners report, you will understand that the delay, see, if you have looked at the timing report, right, it has something called as the delay of each of the cells, okay. Now, if you look at that, the delay which is mentioned over from the 0.6 corner report, right, it will have a higher cell delay, while that from the 0.67 will be at less. So it can happen that your timing is being met at 0.67, but something at 0.6 is not being yet met. So that why when you do an STA, you try to close it at all corners. Okay, that's not something that it is meeting at one corner. It should meet in all corners, because you don't know that. See, your main intended design was to run at 0.67 volt, but it can happen that even at not at this 0.67 can boost up due to something, there is a glitch or something, your 0.67, instead of getting 0.67, the cell can get 0.7 volt as well. Okay, so something that MCMM is a kind of something you can, at the initial you will tell the tool, okay, these are my corners and this. But in the library itself, it goes in the format like, if this is my cell in this corner, it will have this much, for example, my setup time will be this, my whole time will be like this. Okay, so for each of your libraries, you will have different corners. Okay.
Okay. Okay, ma'am.
Yeah. So finally you understood, right? Like it's an overall, this process of explaining is very easy, but when it does through the tool, right, there are a lot of settings and techniques that has to be guided for the optimization, especially. Okay. Mapping can be done very easily because the tool knows, okay, these are my kind of libraries and this I have it. Okay, this is the only thing which I can use. But the main intention behind your synthesis is how do you optimize your tool, optimize your design to meet your PPA targets. Okay. Now, for very simple understanding, is it possible to remove these? Okay. Have you guys looked ever into, have you ever guys worked with very small project? 3-bit adder, correct? Full adder, not half adder. Have you guys worked upon it? Guys, can you just answer it? It's very simple. That have you ever, I'm not taking any complex design because the complex design explaining is very difficult. But just for a simple understanding, have you ever worked with, or you in your, even in your curriculum, have you looked at 3-bit adder? What does an adder do? Can somebody tell me?
No, ma'am.
You have never worked in your digital electronics, you guys never worked with adder, full adder, half subtractor, full subtractor, full
Okay, digitally we know, ma'am. It will add the 3 bits of numbers.
3 bits of number. Okay, I'm saying that I'm doing a 1 bit adder, but for 1 bit full adder I want to design. So what's, how does it look like? Can you just explain, any one of you guys? This is something I'm expecting from you at least. Now don't be smart and you now you go and Google it. You have never looked into a design of full adder? You would have done it lot of calculations, and this is draw a half bit adder and explain full bit adder.
Yeah, it has 3 inputs and 2 outputs.
3 inputs and 2 outputs. What are the 3 inputs?
We have sorry, like 2 1 bits and one, and the other is carry in we have.
Yeah, we have the carry in. Okay.
Yeah.
Okay. Something like this, are you guys able to recall it? Something that you studied during your bachelor's? At least I'm expecting bachelor's would have masters. I'm not sure if they have studied a very high curriculum, but at least this is a design of a full ladder, right? You guys have studied it or not? At least say yes. Guys, I am the
Yes,
one
sir.
who's
Yes,
speaking
sir.
from past 1.5 hours. You have looked it into this design? An
Yes, yes,
adder, a
yes.
full bit adder,
Yes,
right?
I'm
It has
studying
3
with them.
inputs, which is primarily not, the third input is the carry in, but something which is A plus B, and your third is C in. And the output that is being generated is nothing but your sum and carry out, right? Very, very basic thing. Okay. If you're unable to recall it, I'll just say you that I am not going to give the complete calculations and then find it out. Sum is done. Sum is nothing but A. The symbol of plus with a circle outside is called as XOR, right? So sum is nothing but A, XOR B, XOR C in. Okay, if you look at this design, right? I'm first performing an XOR of A and B, and then once this has been given, I'm giving the third input as C and N, and then my sum is being generated. Okay, you're able to correlate it, right?
Yes,
Yes,
ma'am.
ma'am. Yes, ma'am.
Okay, and then the final is carry out. Okay, so the carry out is something which is called as AB plus C in A XOR B, or in when you do it in SOP and POS form, there is something which is called as AB plus AC plus BC. For example, I have, as of now, I'm doing it with this design, saying AB plus C in plus A XOR B. This is the way I have depicted it, correct? This is something which, this is A and B, the first part, right?
Yes, ma'am.
This AB is nothing but your A XOR B. Okay, so this is done using this part, add AND gate. Okay, then A XOR B is already out of here, right? From here, you are again doing an AND gate with the C in. So this logic is being over from this AND gate. Okay, this is second logic. This is first. So this is your first one, and this is your second. And inside this, there was a plus symbol, which is nothing but your OR gate. Okay. So now, I'll explain you in very simple language how does an RTL will look at, then how will your gate look, your netlist look like. Okay. Okay. Since if, for example, if you would have, I assume that everyone should have written this RTL code, but not sure. And let's go. Okay, so the way an RTL is being defined, right? Every RTL begins with something which is called as module and the module name. Okay, now since our module name is called as full adder, I've written it as full adder. Okay, now inside this, you have to define what are your inputs, what are your outputs. Okay, so we had three inputs, right? A, B, and C in. Okay, which are all 1 bit. Then there is something which is called as output. We had two outputs like sum and cout. Okay. Now, if you would have written RTL, you have heard this assign statement, right? So this is something assign sum, which you looked at previous page, right? Sum is A XOR B XOR C in. This is a symbol for XOR, right? So sum is nothing but A XOR B XOR C in, and your out is something which I've stated in your this format, right? SOP format, which is A and B or B and C or A and C. Guys, have you ever written a small RTL code for anything? Or
Yes,
is it
ma'am.
something
We
like,
written, ma'am. We have written.
okay, that's
Very large we have written.
okay. So this is something, this is the RTL person writes it. Okay, this is a very simple example I'm trying to explain you. How will we go from an RTL to netlist? Okay. Now, once this process of complete synthesis is done, right, then you will have something in the form of netlist. And how will this netlist look like? Okay. So this is the way a netlist will look like. It will also have something as module, which is full adder. Nothing will change. It has input A, B, C, and output sum and cout. But now, if you look into it, right? Now it has something which is called as wires. Okay. Wires are nothing but the intermediate outputs. Okay. Input and output are, let us consider to explain you simply, input and output will be transformed to your ports in the real world. Okay. Because this is the way you will provide the inputs. So there will be a port named as A, B, and C, and then there will be some output ports which are named as sum and cout. But inside this, there will be something that internally logic is doing it, and whatever the outputs internal logic produces it will be shown in the form of wires. Okay. I hope guys this RTL, like, this definition is clear up to you, because if I need to explain this will take a lot of time. Okay. If not, then just go and once read like how does an RTL or this very log looks like. Okay. So this is nothing but your internal. Hello.
Ma'am, here in the RTL side, if we have assigned another kind of equation for cout, will we get the same gate level netlist, ma'am?
See, the netlist, I said, right? The complete way the netlist will be generated depends upon the optimization strategy. Okay, it never guarantees, for example, A XOR B XOR C in C. For example, let me say that by mistake, let us say as of now, by mistake, my libraries doesn't have XOR gate. Okay, it have only two universal gates, right? Can't I design, you would have done this lot of things, right? Design an XOR using an AND gate. You would have done it, right? Guys,
Yes. Yeah, ma'am.
So there is nothing that this derived, these are called derived gates, and there is something which is called as universal gate. So the possibilities that my design doesn't, my libraries doesn't have XOR gate, but still tool will understand it. See, RTL person can give it in XOR format. He doesn't know what you're going to do. But the way synthesis will do, it will tell you, right? Hey man, I can do this function using NAND or NOR gate also. I don't need XOR gate. Okay, for example, you are performing if you go to a bigger picture, let's say ALU you're doing, and you are stating that I want to do this using 64-bit operation. He said that there is no ALU 64-bit, but I can do it using 32-bit ALUs. Fine. It won't constrain you saying that I cannot design it, but it doesn't guarantee that if you are here using XOR, you will finally land up using XOR.
Okay, ma'am.
Okay,
So for which kind of gates the tool will give the high importance, ma'am, priority?
see, the way it decides is based on your constraints, right? For
Okay,
example, it will understand. Let's say, if for example, the way it is being designed, right? If you had a simple XOR gate, your design is very simplified way. But if you don't have a XOR gate, now the tool is doing using NAND gates. Okay, so the number of NAND gates will be required will be larger, right?
yeah, ma'am.
So the tool will do it on the basis of the constraints that you have provided. If you don't have any area constraints, see, the tool can do that. Instead of me using an XOR, one XOR gate, I will use 5 NAND gate. Okay, tool can do it. And now it is also meeting your area target. You had a lot of area, you have no constraints. The tool can do it using this. But for example, if you had an area constraint, now let us say your library has all the cells. Okay, and I could have written, instead of XOR here, I could have done it in the using NAND or NOR gates. Okay, now tool will understand, man, RTL person is saying that I can use NAND or NOR gate. I am smart enough. I know optimization thing. I can do it using Boolean algebra and everything, right? You see, in your BTech, you would have done this K mapping, and
Yeah, ma'am.
if you go more method, Queen McCliskey methods, right?
Yeah.
So the tool knows that how to do it. He is smart enough. Okay, along with that, there are a lot of different as I said, right? If you go ahead, we will understand a lot of optimization techniques that the tool will do. Okay, so
Okay, ma'am.
tool is not, he knows, okay, this is the way you can do it. Let me find out, if I have this area constraint, how can I do it in less number of cells?
Okay.
Okay, but just for a simple understanding, I have mapped it from here to here. Okay, now,
Okay,
so,
ma'am.
yeah. Now, if you ever look in your netlist, there will never be an assign statement. If there is an assign statement, definitely it has to be caught at your early sign. There are a lot of sanity checks that the synthesis person does, okay? That he validates the this netlist and everything. Okay, so the netlist should not have any assign statement in it. Okay, so now this is, I have written it in terms of XOR. Okay, see, somewhere was there any XOR or AND related something? No, right? Let me say, for example, this is very basic. For example, it can say I have used, instead of this, I will, okay, it can have, for example, I have not shown it over here. Let's say when you really have a very design from the, okay, it will say XOR. It will say XOR 2, stating that it is a 2-input XOR gate. Then it can state it is okay. It will say E3, okay. And then something, there are a lot of specification. Let me say it will have the name as LVP. Okay, the real standard that the company or industry follows, right? Instead of XOR, it will have something not like XOR, but it will have something like this. Okay, this is what you have mapped your design to a particular specific gate. Okay, so when you read this, see, all of the vendors who does this standard cell building, right? Whether it be Synopsys or it is from TSMC, if you're using something from Samsung, they have their industry standard format, which is not revealed outside because that's a confidential thing. Once you're in the industry format, you will understand. They'll have a complete guide like how to read this. Okay. So for example, basic names conventionally same remain same. So from this you will understand, okay, this is an XOR gate. 2 means how much is the input? It's 2, it can be AND 2 or 2, right? There can be 3 input gates, there can be 4 input gates, like, so it states, okay, 2 is then, it is a 2 input XOR gate. D3, normally it's D3, which states that it has a drive strength of 3. Okay, drive strength 1, 2, 3, 4, it goes depending upon what kind of they have available in the libraries, and this is kind of a VT flavor which we have used. Okay, so now this is something that you're, instead of this is was something which is very high level language, right? This was this, you cannot send it to someone to machine to understand what you are using it, right? And even along with XOR, you could have done a lot of optimization. After optimization, you will have to map it to the particular cell. So then this final mapping cell is present over here. Okay. And I hope you understand that. For example, this states like I am doing an XOR operation. These are my input. Okay. And this is the output. Okay. Internally, this is the N1. Okay. If you go back to the design, right?
Ma'am, that's the instance name or the cell name, ma'am?
Which one?
Or the complete representation you have given, the extension of XOR.
This is your ref name of the cell, right? This is your instance name. Ref name is something which is after instance name, there will be a ref name, but this is your instance name as of now.
Ma'am,
Ref
could you
name,
brief that the reference name, the instance name, and the cell name, ma'am?
okay, that can I do it in the later lectures, because when I'll be explaining you the complete, once you are doing a lab session, right? Once and this is developed, I'll give you a correlation between them.
Okay, ma'am. Okay.
Okay, there is no much big difference, right? See, for example, very small, specifically if I have to explain it, right? Let's say in your, for example, in your library, right? You have something, and let me say it is 3x3. Let's say the naming convention by the companies, and 3x1 drive strength 5. Okay, and let me say it is HVT. Okay, this is something which is present in your library. Okay, now this is whatever cell name is present in your library is nothing but that is called as your ref name. Okay, because that is the way in which you will refer this cell from your library. It is a very standard format. All the cells, the way they are being defined in the library, you have to refer them, and that is called as your reference name. Okay. Now, for example, if your design, let's say, let me build, this is some 3 input AND gate. Okay, A, B, and C. Okay, then it goes through some logic. Let me say it went through some, this is, let me say this is my OR gate. Okay, then this output came and it went again through 2 different outputs, and let's say it went through AND gate. Okay, now let's say this 1 and 2, these are my AND gate. Okay, now when you will read your netlist, right, both of them are this one, but then how will you filter out, for example, which is cell 1 and which is cell 2? So what I have to mention is I have a cell which is A and let me say A and 1. Okay, then I will have my ref name. Okay, and then there is something what it is doing. So now when you read in your design, right, you will have all the you will have all the instance name. Ref name has to do only with your library. When you do a report, when you do that gets, you will do the, give me the ref name of this design, this cell, then the tool will give you, okay, I am this kind of a cell. But for example, okay, now you have to refer this. How will you call this? You cannot call it as and. Okay, in my design I have and 3xd. Then how will a person understand you're trying to explain me whether you're talking about this cell or you're talking about this cell? So you have to call them through that instance, right? This is the instance in my design and that's my instance name. But this instance is linked to a cell from the library which is called as a ref name. Understood? Hello?
Yeah, but how will the reference name will be, ma'am? Like the instance you have given here?
See, very basically, reference name is nothing but whatever in your library is the name the cell has it, right? It is called as nothing but your reference name. The one which is present in your netlist are nothing but your instance names. The tool understands it after your in your design, right? It doesn't only have it has inst name, it has ref name, and then what it is all connected to. It has both of it. It doesn't have one thing.
Okay, so AND gate is the reference here. Is that right, ma'am?
Which one? And one is your and one. I'm referring this as and one and this is and two. And one and two are your nothing but your instance name. And both are belonging to the same reference name, which is and3xd5hvt.
Okay, okay. Okay, ma'am.
Okay, because see, if you refer both of them using this, then how will you explain somebody that this is, see, it is like there are all boys. If I say boys, how will I get to know which boy I am trying to refer to, right? So boys is something which is just a reference name. Now I
Okay,
have to
okay,
say,
yeah, ma'am.
okay, there is a boy which is Akshay, which is also in my class, and there is someone who is also Saksham in my class. Both
Okay.
are in the same class, but see, class 6D, let's say 6 standard division D. Okay, so 6D is nothing but mere ref name. Okay, but Akshay and Saksham are the instances, correct?
Yeah, ma'am.
Okay.
Yeah, ma'am. Got you.
Okay. Okay, so this is kind of this you have been mapped it to your cell, right? Instead of this symbols, which was in a very high description language, you have now came down to finally a design where the tool notes that what gate I am going to use. I am going to use XOR gate. Okay, so the output of this A. Okay, so now output of A and B XOR is stored in the wire N1. Okay, now I have to do an XOR again with the C, right? C in. See, this operation we have performed, and this operation is being stored in N1, correct? Correct, you got it right. This is the first one is what is the output, and the next two are what are the different kind of inputs you have it. Okay, so you understood that A and B are my inputs, and I have to do an XOR with it, and that is being stored in a wire which is called as N1. Now still half the operation is left that you have to again do its XOR with C in. So now it's nothing but N1 XOR C in. So you are performing N1 XOR C in and storing it in the sum. And sum is your primary output. Okay. Similarly, as I stated, right? A and B, B and C in this has to go through performing 3 AND gates, right? 1, 2, and 3. These are performed through AND gates. And then you have to do an OR between them. Okay. So instead of C, it is not doing, if you look at it, right? It is not doing, if you can look, this is a OR 3, right? I have not used OR 2. If you look at it, right? The tool could have used 2 OR gates, right? Now the simplified way that the tool did it, it didn't use 2 OR gate. It does it using OR 3 and pass 3 inputs. Correct? The person who asked me the question, like, will it do exactly the same way? No. He understood that instead of me going to 2 input, 2 OR gates, I can use 1 input, 3 OR gate. Okay. So this is the way the tool has done its optimization and even have mapped it. Okay. There is also a simpler way, right? For example, this is always not the thing. If you look at it, right, the tool can, okay, the tool can also generate an output with lesser number of gates. Okay. I have not explained over here module where everything would remain the same module A, B, C in output. Okay. Now let's say the wire naming, I have changed it as for now. For example, there was no possibility that the tool found it for doing a sum. Okay. But what it does it for, it reduced the number of AND gates for performing the carry out operation. Okay, because if you have looked at the earlier picture which I depicted, right, it shows that instead of AB plus AC plus BC, you could have done it in the form of AB plus C in XOR A and B, right? Guys, you remember this one, the first output where the first way it generated was using this SOP format. And there it found out that the number of gates that can be used are larger. So it had a simplified way, right? It did this and landed up to this one because the tool knows I can optimize it, reduce the number of gates. So let me do that. So now what it does it uses this formula and then it does is this final. Okay. Through some it could not do a changes. But now if you look, right, instead of 1, 2, 3, 4 gates, I am using 3 gates. So look at it, for example, with such a simple logic, if I am able to save one gate, there are such complex design in the way it can optimize, it can save the instance count and for example, let us say in billions or at least in thousands. So once you're saving this, right, you are helping the tool see. You're very clearly that you're helping with the area. Okay. Because once all these cells would have been used in your design, you would have occupied your core area. It helps in reducing the congestion as well, right? Because it will help you that you have a lot of resources which are empty in your core area, and there can be a direct routing, no detour. So it will help you in improving your timing, right? Your speed as well will increase because the tool now doesn't have to route too long. So this is the way the optimization engine works in the synthesis. Like let me, instead of this, the tool has optimized and generated this. Okay. So this is the way an RTL comes, and this is the final way a Verilog will look at it like. Okay. So now moving ahead, this is a very brief overview of what are the way the synthesis goals, or what kind of thing a synthesis engine can do and what are its intent. Okay. Now let me look at the first goal. Okay. So we understood that the primary goal of the synthesis is to get the gate level netlist, and this gate level netlist has to be passed on to the PNR team for the further optimization. Okay, because since here there is no clock information, the way the clock has to travel and everything, right? So that will be done through the PNR state. But I have to at least get the gate level netlist. Okay. The second thing is logic optimization, right? You understood the way the tool has to optimize it. Instead of me using like lot of gates, right? Instead of me having 5 different gates, can I do it and generate the output just in 3 gates? This will help me to achieve my PPA targets. Okay. The next thing which the one person asked is, if for example, if your industry standard works with something called as DFT. This is, see, every industry has a different mechanism. Okay. When I work with Intel, there is a different mechanism. If you work with AMD, there is a different mechanism. There is not sure guarantee that the synthesis and DFT team will correlate and work. Something is, once synthesis is done, it can pass on all the things to the DFT logic. DFT team can do the insertion and then pass it on to synthesis, and they'll do a lot of checks. So what happens in the DFT logic insertion, right? I just, the way I explained you, there is something that they will have the notion like how much flops to convert to SDF, which is, when I say the word SDF, guys, please understand this is nothing but scannable D flip flops, scannable flops. Okay. Normally D flip flops is the one which is majorly used in the industries. Okay. So
Ma'am, after inserting the scan flops, will that be an input again for the synthesis, ma'am?
yeah. It will again, it can have, and we can provide, see, as I stated, right, this is the way of mode of working between the organization. Okay. If the way that your company works is, they will have, okay, I'll give the input to the DFT team. Once it does the insertion, it can pass directly to the PNR team. If it gives us back to the logic, we will perform some primary sanity checks are there, that okay, have they provided us this input? There is nothing which is wrong in their dev that they have been, there is nothing, that just more majority, the primary input that we get from DFT or this team is nothing but your Scandef, stating how much logic has to be converted into your SDF. Okay. If you get it as a part of a synthesis, you can perform a resynthesis, okay, an incremental synthesis using compiler, command, so that now you'll have, okay, if I have this kind of a thing, how can I perform scan chain reordering, right? If you're doing a physical aware synthesis, as I stated, right?
But
Then you
we
can
do
change.
reordering in the PNR stage also, no, ma'am, during placement stage.
That is also possible. See, there is a technique, whether you are doing it at PNR state, it is also possible. For example, if you are already doing a physical aware synthesis, you can also do a scan chain reordering, correct?
Okay.
So this is the way that it depends upon company to company, the way it is being done. But the main intention behind your DFT logic insertion is, they have some algorithms and they find out how much should be the test percentage coverage. So they'll explain you that, okay, this logic, please try to make it as instead of DF, convert it to SDF. Okay.
If the scan chain reordering is done in synthesis, ma'am, then it cannot be repeated in the PNR stage. Is that right, ma'am?
No. This is not such thumb rule. See, I stated, right? It can happen that, for example, when you are doing it at your stage, I am not sure whether the PNR folks, see, work at very high level language, at very high level companies, right? It can happen, for example, the way I was making the logic being said, there is a changes in the port placement. Okay, let's say that, for example, there was some changes in the port placement and this information directly came to the PNR folks. Now they change the port placement, so they do have to change their logic placement, right? Some logic would move near to that port. Now happened that when you're moving this logic here, whatever scan chain flops were there, you have moved it. So again, you can reorder it, right? You can enable that app option. There are this way to guide is like you can enable the app option stating that, okay, you can do my scan chain reordering. Okay, when you're doing a legalized placement itself, right? During the placement stage also, you can define the tool. Now, please, you can enable this app option or the setting during your placement as well, so that the tool will do the scan chain reordering at that place also. So there
Okay,
is
ma'am.
nothing like if you're doing it synthesis, you can't do it at PNR. You can
Okay,
even
okay.
you can enable at PNR, and it is enabled at PNR at your placement while doing your placement activities.
Okay, ma'am. What I'm thinking is like if it's done in synthesis, then time we can save the time during PNR is what I'm thinking.
Yeah, but
But
I'm saying that
placement,
there is no short guarantee that whatever placement you have. See, you can also dump a def and give it to them. Okay, there are industry standard that synthesis team can give us a def. Okay, but for example, the way you did an analysis and the person wants to say that I don't want to go with this def. I have the netlist. Let me try my own placement, right? Because see, at when synthesis stage, you are not sure like how much hard macros they have in their design. Like for example, a design will have a lot of memories in it. See, there can be a lot of analog logic, there can be PLLs. The way they are sitting, you are not sure, right? If you are see, it happens through a trial mechanism. It goes through a lot of stages that once your placement is being fixed. Okay, that during my early trials, I made a lot of things. I made analysis that, okay, I have to make this hard macros placed in this and this location. Then you can dump a def and give it to the synthesis team. It is back and throw method. Okay, but at the initial, when you're giving it a try itself, okay, you're starting the synthesis, you don't know that the netlist which is going to that person will have how many, where will he make the memory set in the design, where he will make this analog logic, this PLL logic, right? So the way the placement can change. So now if you have the very hard constrained def, so there is something that the tool cannot optimize it, and it will again result in that zigzag manner. Okay, so you have to enable it even at your PNR stage as well.
Okay, ma'am.
Okay, and then something which is clock gate insertion. This is also something, see, clock gates insertion can even happen at PNR phase, but this is something, for example, I would have explained it in my last lecture, right? You know that what is the, like, what and essentially is clock gate is, right? It is basically, clock gates are nothing but to gate your clock being traversing in your design. There is a special cell which is called as the ICG cell which does this task, right? But you, for example, if you know, okay, this is a kind of uh, see, when you read it through when the RTL folks get this design, right, you get a notion, for example, that after this and this, like I don't need my clock to be propagated after this one clock cycle, I need the clock to be propagated after 6 clock cycles, so I can make the my logic turn off, I can turn off this flop for 6 gates, right? Because otherwise what will happen is 6 times your clock will be toggling. And as a flop, the main intention of the flop is every time the clock toggles, it will keep on passing the input. But as a designer, we knew that at least for 6 clock cycles, my input will remain stable to 1. Then why am I making the flop toggle? Because if you look at the power dissipation of dynamic power, right, it is like alpha f c VDD square. So alpha is like how much time your gate activity is happening, right? And F is your frequency of the clock, C is your capacitance, and VDD is here. So I have to reduce this alpha, right? Don't switch it multiple times because I don't need it. My data is stable for at least 6 clocks. So this is also something that you define it, and this is the way the tool understand and develop this logic and give you an ICG cell, ICG, or call it as CGC. This I can explain you in very detail in the later when we go through it. Just for an overview, I gave it like this. Something which is not functional accuracy. See, functional accuracy is nothing but, for example, it is done through something which is called as LEC, or it is called as functional verification. LEC is a tool which does it. It is nothing. See, When you understand the synthesis, you understood there was something which is called as RTL, and there was an output which was called as netlist. Now, for example, when you're doing this process of synthesis, you should not alter the intended functionality of the design. Okay, let me say, for example, when you manually tried to alter, like, for example, there was something, let's say, there was, let me say, very simple combinational logic. Let me say there was some AND gate. I'm not showing all the input just for this. There can be an AND gate, there can be an OR gate, then there can be something else. Let's say there was, let's say, let me say, there was inverter connected, inverter and back to back inverter. Let me say, okay. Now, for example, you opened up manually a design and thought like, I will try to optimize it. And you were doing some primary timing stuff to check it whether if I can change this inverter to, for example, I can increase this drive strength and check whether my path is being met or not. Let us say by default, you replace this inverter with a buffer. Okay. Now let's say that the input over here was 1. Okay. Now the output was 0. And now the output was 1. Okay. But now since you, let's say this buffer, I'm giving it a name, that this inverter was 3. Now you by mistakenly, it can happen. Okay. By mistakenly, you made the changes from an inverter to a buffer. Okay. Instead of turning this inverter from 2D drive 2 strength to 3 strength, you made it a buffer 3 strength. So what happens? Now the design is 1. Now it is not an inverter, it is a buffer. So again, output will be 1. And now their output is 0. So what has happened? Your complete functionality has changed because of some goofing up with this cells, right? So what happens is every time when you do it, right? Even this is something which could happen manually. We have to cross check if tool did not mess up with something like this. Okay, so you have to maintain this functional accuracy and you have to do it through LEC. So the LEC has two inputs, primarily input which is called as golden input, which can be your RTL, and the revised size is nothing but the netlist you have done generated through your synthesis process. It has a very vast method. If you go inside LEC, it has complete detailed description what happens to each of this, how does the tool does this comparison, but the basic overall understanding it will check that whatever the RTL was intended and whatever the netlist is being generated, they are exactly same. There is no functionality changes that has happened in this process of synthesis. So that's also your primary goal that you have to meet it. Okay, because what happened is you made this blunder and you passed this complete, this is I'm saying with a very small perspective, and without checking the LEC you passed it on to the PNR team. The PNR team takes it forward to the routing and this complete intention of the design has itself changed, right? Because what happens, the PNR folks will, what they will do is they will check with your netlist. They will do this LEC at each step, or at the end after routing, what will do, they will compare that what after routing, they will take the netlist and they'll compare with the synthesis netlist. But synthesis folk did not do a thorough check. Now they will pass it because their routing netlist and your input synthesis netlist are matching. But it is a primary responsibility of the synthesis engineer to first check it whether I am matching with my RTL. Okay. Along with this, the final thing which is the constraint handling. Okay, the kind of way I have passed it on to my inputs, am I meeting the target? You will do it like after you check through a lot of reports, like how is my timing, have I met the timing or not, are there any setup or hold violations. You will compare your area number with the budget you have defined in your project. Am I meeting the power targets? So these are the things that the constraint that you have passed are being primarily met or not. Okay, so this is the overall view of like how does the synthesis try to achieve this lot of goals. Okay, so just winding it up, I'm just saying that the synthesis steps which I have covered is nothing but first is what is called as translation. In this, you convert your RTL into general logic gates, where I said, right? It will do a just raw optimization, nothing raw conversion, no optimization. It will just convert your, for example, A and the way you have written ampersand B, it will just convert it from that language to generic logic gates. Here I have used the word generic logic gates. Okay, this is still independent upon what type of gate I am going to use, whether I am going to use with extend 2, 3 VT flavors, 2 inputs or 3 inputs. That is not yet done. Next is how will I optimize it to meet my target. So I will use my SDC constraint and look into the library and try to optimize it so that I meet my PBA targets. And finally, there is something which is mapping, which is technology mapping, right? From that, I will map it to what is the library I have it, whether I can use lower drive strength, high drive strength, what are the things I can use. And then finally, my netlist is being ready. Okay.
Ma'am, excuse me, ma'am. Ma'am, LEC is done at the post synthesis and as well as the post PNR, ma'am. Is that correct?
See, the LEC has capability to do a check between RTL to netlist, and it has the capacity to check between two different netlists. As a synthesis engineer, what you will do is you have input as RTL and you have generated your synthesized netlist, which is your netlist, gate level netlist. So as a synthesis engineer, what you will do is RTL versus netlist. Now, this is post your synthesis, correct?
Yeah, ma'am.
Once the synthesis is done. Now, when the PNR folk does it, right? PNR folks has the capacity to do it even after all the stages. Okay, they will do a comparison between your synthesized netlist and, for example, that let's say their placement activity is being done. So the placement netlist is being done. So they can do it between your synthesized netlist and placement netlist. Now let's say that has passed. Now they have gone to CTS stage. Okay, they can do a netlist between placement netlist and your CTS netlist. They can even do the CTS netlist with the synthesized netlist, but the drawbacks is, see, the way the design gets matured, it has to do a lot of iteration to check it. Okay, and the time duration when it does it between a synthesized netlist and a CTS netlist can be high, while the one which you do comparison at placement versus CTS will be lower. Okay, because there very minimal changes has been done in the design, right? There is no constraint that you cannot even, you can at the end you can even do a LEC between the RTL and after the routing netlist as well. Okay, but the only thing is that they see it takes lot of hours to do it. Okay, this is not very simple process that you can get the result. For complex design, it takes 8 hours, 10 hours, 12 hours. So we are always on the verge of like how, see, time to arrive in the market is also something which is of great importance, right? If you can do this project for at least 1 year, you do it, but the race is important. For example, if the Google launches the phone before Samsung, it can have a drawback because people will go. So the way we are trying to save our timings, right? There is no constraint that you cannot do at any stage. Post synthesis also you can do, every stage of PNR also you can do this.
Yes, ma'am.
Okay.
Yeah, ma'am. Yeah, got you. Thank you, ma'am.
Yeah. So this is finally the top model of the synthesis, and finally I'll like to conclude it what we have done through the synthesis, right? So synthesis is nothing but it is a process. When you understand it is a high level technology independent, just understand it. I would always say that understand it with respect to this wordings and correlate and visualize it with the examples. And see, when I try to explain you either through an example of chef or through an example of building a, so this is nothing which is a rocket science, right? Try to understand and correlate and visualize it, how it happens in the real life. Okay, when you're saying high level technology independent, understand each of this word, why it is being called as high level, because something this is not been understood by the tool. This is something which has been understood in the human readable format. That is why it is a high level abstraction language. It is technology independent because we don't know whether the XOR operation that I'm going to perform will use XOR gate or will it use an AND gate, what kind of, from which technode it will use, whether it can be used from 3 nanometer, 5 nanometer. So it is all the cells I'm still using is independent. Okay, it is written in Verilog and VHDL, and then the synthesis will do and convert it into a gate level netlist. Okay, which is technology dependent. So understand each and every word of it. We looked at what are the main basic steps, which is called as stop, translation, optimization, and mapping. What are the different inputs and outputs we have? And then what is the importance? Why did we do this, right? because we want to make the VLSI world understand it only in terms of gates, wires, transistors. It doesn't understand the operation you have read, what is plus, what is ampersand, what is OR. Okay, and the way it is important is because how I'm going to optimize it. This is something, the main importance of synthesis optimization. Otherwise, it could have been done in a very simple format. Like you could have just grabbed the RTL, convert it into the gates which you look, and it is done. But the main intention behind synthesis is complete optimization strategies. As and when we proceed further, I'll explain what are the different various strategies involved in it. And the main intention is to meet your PPA target, which is power, performance, and area. So that's all for today's lecture.
Thank you, ma'am.
Anyone have any doubt? Anyone have any doubt? Okay then. If anyone have any doubt, they can WhatsApp to me. My WhatsApp number is written in the in the channel also. Okay then. Thank you. Thank you everyone. Thank you.
Thank you, ma'am. Thank you.
Yeah, thank you.